Alright, in this video we're going to look at a car moving around a corner. This could be like an on-ramp to a highway or something like that, but this corner is not banked. So this is just going to be a flat road that's turning, and we're going to figure out what coefficient of friction is required between tires on the road to allow the car to stay in that circular path or to accelerate around that curve at a constant speed. So a car travels around a corner with a radius of 15 meters. That means if we imagine the road and the curve in the road were a part of a circle, then the radius of that circle would be 15 meters at a speed of 40 kilometers an hour. Assuming the road is flat, what is the minimum coefficient of friction that will allow the car to make it around the corner? So first things first, 40 kilometers an hour needs to be converted into meters per second. For every 1 meter per second, it's 3.6 kilometers per hour. You can look at previous videos if you want to see this conversion, but it works out to 11.1 meters per second. So the acceleration of this car is given by v squared over r is 11.1 meters per second squared divided by the 15 meter radius. So to keep in this turn, the car needs to accelerate at 8.23 meters per second squared. Now, if we imagine looking at the car from the back, I don't know, that's a car, whatever, and it's curving around a road that goes like this, the force of gravity would be pointing straight down. The normal force would be balancing that. And it's really only the force of friction between the tires on the road that can be pulling it towards the center of the curve. So what we're assuming here is that the net force that's causing this acceleration is a force of friction. In this case, there's nothing funny going on, so the force of gravity is equal to 9.8 times the mass of the object. And the normal force is also, at least for its magnitude, equal to 9.8 times the mass of the object. And so the force of friction is equal to the coefficient of friction times the normal force. And we can put those guys in here. So the force of friction is equal to coefficient times 9.8 m. And the net force is going to be, according to Newton's second law, equal to the mass times the acceleration. Now recognize that mass is on either side of this equation. Can't equal 0, can cancel it out. So I've got 8.23 meters per second squared is equal to mu 9.8 meters per second squared. I can divide both sides by 9.8. And I get a coefficient of 0.84. Now, keeping in mind this force of friction would be the maximum coefficient of static friction. So really, any coefficient of friction that's greater than this 0.84 will be able to provide this 8.23 m force of friction that's required to keep this acceleration going. So really, any coefficient of friction that's equal to or greater than 0.84 should be able to keep the car into this turn. So, first we calculated the acceleration using the details regarding the circular motion, keeping in mind that kilometers per hour need to go to meters per second. Using that acceleration, we found an expression for the net force. We recognized that the net force was being created by a force of friction. Since we can come up with a normal force, we can make an expression with the coefficient of friction. Force of friction is equal to coefficient times normal. We substituted that in, both our acceleration and our expression for the force of friction, solve for the coefficient of friction, and then recognize that that's a minimum value due to the fact that the force of friction can be anything from this maximum value down to 0 as needed given the situation.